Okay, so in the last lesson, we learned about the properties of parallelograms, meaning if we have a parallelogram, here are the things we can assume. Now we're going to switch over a little bit to the converse of all of those, and that is here are things we see. Do those things prove that there is a parallelogram? Okay, so that's what this is. 5 ways to prove if quadrilaterals are parallelograms. Okay, and there's 5 of these. These are in your notes. We did not fill them in class. I sent pictures of them, but I wanted to also go over them with you on the video. Okay, so the first one is related exactly to the definition of a parallelogram. It's just reversed a little bit. Okay, so we're going to fill this in. Let's see. Okay, so this one should read, if both pairs of opposite sides of a quadrilateral are parallel, then the quadrilateral is a parallelogram. And again, that's just related to the definition. So, for example, if a shape was drawn and the only markings that were given on the shape were the parallel line arrows, and it showed 2 sets of those arrows, and you were asked to tell if that was a parallelogram, you would say yes. Okay? Because this actually says if all that you see are 2 pairs of opposite sides that are parallel, then that is enough information to prove a parallelogram. Okay? So that one's kind of an easy one because it relates back to what we learned already about the definition of a parallelogram. Okay? All right. So the next one actually is the converse of the theorem that we had at the bottom of page 71, the bisecting diagonal theorem. This is the converse of that. Okay? So rather than saying if a shape is if a quadrilateral is a parallelogram, then its diagonals must bisect each other, we're now going to reverse that. We're going to say if we have a shape and it's a quadrilateral, a 4-sided figure, and its diagonals bisect each other, then it has to be a parallelogram. Okay? So, again, if a shape is drawn, diagonals are drawn in, and you see these markings, and they wanted to know, is that enough information to prove that this shape is a parallelogram? The answer would be yes, it is. Okay? All right. Okay, so the next one involves something a little bit different. We don't have to have, this one's its own theorem by itself. It's not the converse of anything else. And that is called the congruent and parallel sides theorem. Okay, so this one's a little unusual, a little different from the others because we didn't have any theorem like this before. This theorem states that if you have one pair of opposite sides of a quadrilateral, if one pair of opposite sides of a quadrilateral is both congruent and parallel to each other, the same pair, then the quadrilateral is a parallelogram. So let me give you an example. If the parallelogram, or if the quadrilateral, I should say, because we don't know if it's parallelogram yet, if this quadrilateral is a parallelogram, okay, or if we want to see if it's a parallelogram, we can prove that it is if we have a pair of sides that are parallel and at the same time we have congruency markings. But it has to be the same pair, okay? So this one would be yes. Now, they might try to trick you and do this. That would be a no. It has to be the same side, same two sides, showing that those same sides are parallel and congruent. Can't be one pair is parallel and the other pair is congruent. It has to be the same one like this. Okay? So that is enough information to prove that a shape is a parallelogram. All right, now let's come back to some of the converses. So the next one is the converse of the congruent opposite sides theorem. Okay, that was the second one on page 71. So instead of saying if a shape is a parallelogram, then it must have opposite sides congruent, we're going to state the converse of that. Okay? If both pairs of opposite sides of a quadrilateral are congruent, then it's a parallelogram. Okay? So if it shows this, is that enough information to prove that this shape is a parallelogram? The answer would be no, because both pairs have to be shown. So they would have to say this and this. And since they didn't do that, if they only showed one pair of opposite sides congruent, then that would not be enough information to prove that the parallelogram is, or that the quadrilateral is a parallelogram. Okay? And then the last one is the converse of the congruent opposite angles theorem, which is the second to last one on page 71. The second to last one on page 71 said that if a shape is a parallelogram, then its opposite angles are congruent. Now we're doing the converse of that. We don't know if it's a parallelogram, but if we can see by the markings that both pairs of opposite angles of a quadrilateral are congruent, then the quadrilateral must be a parallelogram. Okay, so how do we show that? Well, here's a shape. So if you see this and this, then yes, that would be a parallelogram. Okay? If they only show one pair though, okay, so let's say it just says this, and the answer would be no. It has to be both. So those are some of the ways that we can prove that a shape is a parallelogram. And on your homework, it is going to ask you to look at the markings on one of the shapes, okay, and to determine if that makes them be parallelograms. Okay? Okay, now this can apply a little bit more when we are dealing with application of these. Okay, so I'm going to clear this. And I'm going to do an example. I'm going to do example number 1 on page 305. Example number 1. Okay, so there's a shape drawn in there again. It's labeled M, N, P, and L. And you see some diagonals in there. And here's the information that we see written in there. So we have 2y minus 7 y plus 2. And then we have 3x and x plus 5. And it says in the directions, find the values of x and y for which MLPN must be a parallelogram. If this is supposed to be a parallelogram, then what we know is that the diagonals bisect each other. Therefore, I should be able to do these and find the value of x and y. So very similar to what we just did in the last video. So we have 2y minus 7 equals y plus 2, and I'm going to solve for y. So I get y equals 9. And then I'm going to do the exact same thing, but I'm going to do it for the x's. 3x equals x plus 5. It gives me 2x equals 5. Now this one's a fraction, but that's okay. X equals 2/5. So if this is a parallelogram, y has to be 9 and x has to be 5/2. Okay? All right, let's do one more. We'll do like the check understanding for that same example, example number 1 on page 305. All right, and then some things that are written in there. So this one has two things. So we have these two angles here. So if you remember what we know about the angles of a parallelogram, we know that opposite angles are congruent, but we also know from our properties that consecutive angles equal 180. So this one and this one have to add up to 180. So that's what I'm going to do. A plus 40 equals 180. And let me combine like terms first. This is going to be 2a plus 40 equals 180. So when I solve for a, I'm going to get that a is 70. Now let me do the same thing, but this time let me do it with these two sides right here. Again, these are opposite sides, and if we have opposite sides that are congruent, then we have a parallelogram. So if I'm trying to make this be a parallelogram, then I'm going to set them equal to each other. And I get that C equals 2. So these are the values of A and the value of C that have to be exactly these numbers in order to make this work out such that these two are supplementary and those two are congruent to each other. And by doing that, I will prove that they are a parallelogram. Okay? Okay. The next video is going to be the notes from page 73 in your notes.